to finish their coffee. So please just finish your coffee. And I don't know if Moshe will join or he's watching online. I don't know if you got his email. One participant has been tested positive for COVID. So we advise you to follow all the instructions. Moshe provided them. So, please do test positive, because if you are, no, please do not test positive. Please do test yourself. And if you're positive, so this is like example of the wrong short concatenation of the words. And if you're positive, please stay at home and inform us so that we know. So that's the important thing, right? And also wear masks for your own protection. And that's one thing. So this is like practicality. And the next thing that we will start talk with Kuldeep's talk. We will start with Kuldeep's talk. So Kuldeep will talk about functional synthesis. So please, Kuldeep, go on. Usually we don't have introductions, so everyone knows everyone here.
All right. Good morning, everyone. Thanks to the organizers for inviting me. I'm going to talk about the problem of functional synthesis and an approach that we have been following based on combining machine learning ideas with automated reasoning. And Akshay is going to follow up with another approach to functional synthesis. So on a high level, the problem is we are given a relation. So this is a relation specified in terms of a Boolean formula. That will be the focus for today's talk. It's our inputs X and outputs Y. And what we are interested in designing is to design perhaps a circuit that can take these inputs X and output Y so that X, Y satisfy this relation. Formally, we can think of for each of the Y's, we want to figure out the functions for each of the Y's in terms of X. The problem can be formalized as I just mentioned. We have a relation over X and Y. We want to compute a vector of these functions so that if it is the case that there exists some Y for a given X, so that phi of xy holds true, then it should be the case that if we were to substitute Y with f of x, phi of the relation would hold true. This is, of course, very well-known notion. Each of these functions are called column functions, named after famous logician Column. And this set of function vectors is called column function vector. So the kind of problems we are interested in, we have about 2 to 10,000 x variables and 1 to 5,000 y variables. This is where the scalability of the tools can handle right now. Since next 30 minutes are going to focus on this problem statement, perhaps it's a good point to ask any quick question about. These are from the benchmarks. Yeah. Okay, so phi is going to be a Boolean formula over x and y set of Boolean variables. We want to find this function vector. So that is the case that for every x, if there is a y that can make the phi hold true, then it should be the case substituting y with f would make the phi to hold true.
What do you mean find these functions? What representation do you want them? As Boolean formula or?
Yeah, as Boolean formulas. Yeah. Okay. So one thing I do want to emphasize here is that the problem is hard and interesting in the case when phi is a relation, not a function. So what do I mean by that? For assignments for a given assignment to x, there might be many possible valuations of y that satisfy this phi. So here's a simple example. So consider the phi that is x1 or x2 or y1. What can be a possible column function? So maybe you could kind of look at it and technically guess that the column function can be negation of x1 or x2. Let's check if it is true. Well, we can substitute y with negation of x1 or x2. In that case, phi just evaluates to constant true. And it is also the case that for every assignment to x1 and x2, assigning y1 to 1 would make the phi to be true. So in that case, this is indeed a correct column function. But as I mentioned that for a given value of x1 and x2, there can be many possible evaluations to y. And that means there can be many possible column functions. For example, not of x1 is also a correct column function. Not of x2 is a correct column function. Constant true is also a correct column function. And the hardness in solving this problem does come from the possibility of having many column functions. So if there's only one column function for every variable, then you can rely on interpolation-based approaches to extract these functions.
Not one, but constantly many. What if is it a tractable problem?
Now, in that case, also you have to go through something like this. So, all right. So, why do we care about this problem? Well, it's one is a very well-known fundamental problem. But if you have these column functions, of course, you can do quantifier elimination. This has also been very well studied in design automation community. So there has been a long line of work that comes from circuits, symbolic transition relations, and also you can think of program synthesis in the case when the theory is restricted to Booleans and there are no restrictions on the grammar, then this is the problem that we are interested in solving. So there are also diverse set of approaches towards solving this problem. When we got into the problem, there is a long line of work that comes from proofs of validity, input-output separation. Akshay is going to talk about the approach based on knowledge representation and incremental determination. So there's a long and diverse set of approaches towards solving this problem. And as you can guess, that scalability still remains the major challenge here. And I'm going to discuss an approach that we took that does try to address some of the scalability challenges. So this is an approach where we combine ideas from constraint sampling with machine learning and formal methods. And we call the tool Manthan. So most of the work that I'm going to discuss form the basis of PhD thesis of Priyanka Golia, and who was co-advised by Subhajit Roy and myself. And along the way, we collaborated with Frederick Sulwowski from TUVN. So let me give a high-level overview of the approach. So we start with the formula. The first step is to generate the data. If we want to use machine learning, then we want some way of being able to generate the data. So this is where we are going to rely on constraint sampling. Once we have the data, we are going to treat this as a classification problem. So we are going to use very standard off-the-shelf classification tools like decision trees. And once we get these candidate functions, of course, as it is the case with machine learning methods, the function that we have may not be fully accurate. So in that case, we'll have to do a loop to check whether these functions are accurate. If they are not correct, then we have to go through a repair loop. And as it is the case in most of symbolic reasoning methods, pre-processing is very crucial, but I'm not going to discuss here. Right, so let me give a quick high-level overview of how the approach works. We start with a formula over a set of Boolean variables. We sample solutions of this formula. So now we get a table that looks like this. Here are the columns for inputs and outputs. And each of the rows are samples, which are the satisfying assignments of the formula. Once this looks like a table, we can now think of this as possibly a classification problem. So we can try to learn decision trees for each of the y's in terms of the inputs. Once we have learned the decision trees, looking at a decision tree, we can construct the function. Once we have these functions, we are going to go and ask, are these the correct column functions? And thankfully, it happens that this can be checked using a set oracle. So we can invoke a set solver. If the formula is satisfiable, then we have a counterexample. In that case, we go through the unset core. We repair the counterexample. We keep going through this loop until we converge. And at that point, we know that the functions that we have are indeed correct column functions. Okay, so now I'm going to go into give you kind of bit more details about each of these three steps. So the first step is that we have these formulas and we have to sample solutions of these formulas. As I mentioned a real challenge here is the multiple valuations for the y's. So it's not a function, it's a relation. So in particular for assignments to x, there can be multiple assignments to y's. I just extended the simple example we had. So in this case, let's say we added one more clause. So that would mean that when x1 and x2 are 0, 0, y1 must be 1. And when x1 and x2 are 1, 1, y2 must be 0. But for the other possibilities, y1, y2 can take any values. So how do we do sampling? And in this case, it turns out that just doing uniform sampling is not a good idea. And we had to rely on weighted sampling. So weighted sampling is where you can assign weights to the variables. And then the weight of generating a satisfying assignment is proportional to the product of the weight of literals. So uniform sampling is a special case where you assign everything as weight 0.5. So how do we use weighted sampling? Well, we are kind of trying to figure out what are the natural inclination for the variables to take values. So when both values are possible, which value the variable should take so that the corresponding column function will be easy to synthesize. So we have some heuristics. Initially, we generate this set of samples. From this set of samples, we compute these weights, and then we generate the samples according to this weight. So that's how the first step goes, which is to generate the data. And now we have generated the data, we can now treat this as a classification problem. So we have the data of this form. We can try to learn each of the output variable in terms of input. It turns out that it's often a good idea that we would like to learn a output variable in terms of inputs and possibly some other output variables, as long as there is no cyclic dependency. So y2 can depend on y1, and then we would want to make sure that y1 does not depend on y2. Now, if we want to learn each of y2 in terms of the other variables, then we can treat these as the set of label features, and this is the label. So this is really a binary classification problem. There are lots of tools out there that can handle binary classification. What we did is to rely on the simplest tool out there, which is scikit. So scikit is a very popular Python library. So we just use the scikit. Scikit goes and generates these decision trees. Once we have a decision tree, we can extract the function by making a walk through all the paths that lead you to, let's say, all the leaves as assigned as 1. And that allows us to construct these functions. This is just a decision list representation of a decision tree. So this looks like if path 1, then 1, if path 2, then 1, else it should take value 0. Something I do want to point out that this is a one-level decision list. What I mean by that, you can reorder P1 and P2 because in decision trees, all the paths are mutually exclusive. Something that was very interesting here for us is that how should we do learning? So should we allow, typically in machine learning settings, there is a concept of noise. When you generate the data, there is often noise associated with it. So you don't want to overfit. But here there is no noise. Every solution that we have generated is indeed a solution of the formula phi. So should we allow the training, should we allow some training error, or should we go for the overfitting? Well, it turns out that, remember, it's a relation, not a function. So we only have some potential values for a given set of feature assignments. And it turns out that allowing errors is way better than not allowing errors. So that was a bit of a surprising fact to us. So we allowed training error, which means that the trees we have learned may not be consistent with the data that we already generated. So we had to potentially go and repair them later on. Finally, how do we go?
Excuse me, can you explain how is it better? Because
yeah, so I mean, we have some intuition about it, but I think this requires much more investigation. One idea is that because it's a relation, so it means that for some assignments, there can be many other possible valuations. So you don't really want to force yourself to stick with the valuation that was generated by the sampler. And
So maybe clarification. So you chose scikit-learn, right?
yeah,
So it has under the hood cart algorithm.
yeah.
And it can generate all kinds of trees for you. So how do you choose what tree is a good tree for you, and what is your objective, let's say?
Yeah, so that's a very good point. So here we are somehow treating that there is a noise here in the data, even though there is no noise. So what we want is we want shorter trees. So we in scikit you can use this Gini impurity to say that don't go and try to overfit. So we tune with this Gini impurity parameters to not get a large tree. So we are trying to get short tree. What we really want is a tree that would be possibly easy to repair in later stages.
So yes, so that's what not clear. What does it mean? Because if you can train also optimal trees with respect to size, right, without using cart but some other algorithms, and optimal trees can also be of different shape.
Yeah, so
but all accurate.
Yeah, we can discuss more, but it turns out that's what we went initially with, trying to train optimal trees, and that does not work at all. So let me come back to the experimental results. So it took us, this insight cost us few months, because we thought that it's a good idea to learn optimal trees. You already generated the data. What's the point of allowing errors?
So the tree is a function, right?
Yeah.
But the data might not be functional. So you kind of have to accept that there's going to be error no matter what, right? Because you might have different inputs to this, or different outputs for the same input.
Yes, but we are interested in learning only one function. So,
okay.
Yeah. Right. So finally, how do we check that these candidates that we have are correct? So thanks to a very nice observation in 2015, we can construct this what is called the error formula. So let me quickly give you the intuition. So what does this formula say? It says, is there an assignment to X and an assignment to Y so that the phi is satisfied? But if you were to plug in the output of the candidate functions, then phi would be falsified. So is there some assignment where the output of the candidate function would falsify phi, but it's possible to satisfy phi? If the answer is no, then of course these are the correct column functions. But if answer is yes, then we got a counterexample, and we can go and repair with respect to this counterexample. Traditional idea is that you get a counterexample and you go and immediately repair with respect to the counterexample. That turns out doesn't work very well here. Why so? It's always about we have a relation, not a function. So let me illustrate again. So suppose this is the counterexample we have. It says that when x1 and x2 are 1, 1, then assigning y1 and y2 to 1, 1 would satisfy the formula phi, and our candidates right now output as 0, 0. So one would say, okay, I should repair the function for y1 and also function for y2. But what if I told you that there was another counterexample that could say that when you assign x1 and x2 to 1, 1, it's possible to satisfy the formula phi with y1 assigned to 0 and y2 assigned to 1. And if I knew that, then I would not go and repair the function for y1. Remember, it's a relation. So for every assignment to x, there can be multiple possible valuations to y. So how do we go and look for such a counterexample? So what we can do is we can invoke a max set solver to find nicer counterexamples. So what we want to say that here's my specification, here's the assignment over x. Find me the counterexample that can agree as much as possible with the output of the functions I have. Okay, so that I don't have to repair much. In practice, it matters that this is a very simple max set query because a lot of these are unit clauses, so it can propagate very fast and one can solve it very efficiently. So now we get a nicer counterexample from the max set, and we are going to repair with respect to that nicer counterexample. How do we do the repair? Well, let's say now we work with our nicer counterexample. We had to repair the function for y2. One possible way to repair is to say that if x1 is 1, x2 is 1, and y1 is 0, then y2 should be 1. So if a set of literals, then y2 should take a certain value. As you can see, it would be nice if we could have this counterexample that would have a smaller set of literals so that potentially it could fix other counterexamples. How can we find such a smaller set of literals? We can again rely on unset core. We can construct this another formula that says that, look, for x1 as 1 and x2 as 1 and y1 as 0, I really want y2 to be 0. Of course, this is not possible. That's why we have a counterexample to deal with. So the solver comes back and says that you are crazy, you can't do this. And let me tell you, it's not just the issue with x1, x2, and y1. Even if you, let's say, had x1 to be 1 and x2 to be 1, you would not be able to assign y2 to 0. We take this output of the solver, which tells us we are crazy, and we flip it, and we get the repair out. So what's going on? We started with a decision list, which was one-level decision list. So you could flip the orders of these paths. Now we are doing the repairs. All our repairs look like if beta 1, then 1, else if beta 2, then 0. And it turns out all these repairs are sound. So you can also flip the order of these betas. So from machine learning perspective, what happened is that we learned one-level decision list, and then our repair takes us to the two-level decision list. We know from theory that a lot of functions can be succinctly expressed in a two-level decision list, but would require a large representation in one-level decision list. So that's what is happening from learning theory perspective. All right, so this is how the entire approach works. We start with the formula, we generate the data, we learn the candidates, we go on to check whether these candidates are correct or not. In that case, we first check the satisfiability, we get a counterexample. When we get a counterexample, we look for a nicer counterexample using a max set query. Once we get a nicer counterexample, we use unset cores to repair it. We keep going it until we reach where we have gotten the correct column functions. So I did promise you that we came up with a very different approach, but that alone doesn't mean that it's a good idea. So we have to see how well it works in practice. So we took the same set of benchmarks that have been used in the past to evaluate different functional synthesis engines. And we compared it with the state of our tools. So these tools are over a period of 5 years. This is the cactus plot. I'm sure a lot of us are familiar. On y-axis, we have the runtime. On x-axis, we have the benchmarks. A point here indicates that the corresponding tool could solve 250 benchmarks, each of them in less than 800 seconds. So over 5 years, you can see the improvement range over about 80 instances. The tool that I discussed today, we can solve almost every instance that can be solved by any of the other tools. A significant improvement over what was possible earlier. There are some things here worth pointing out, that there is a bit of a startup time because you have to generate these samples, you have to learn, and then go on to repair, which sometimes can be avoided by other tools. So there is still quite a bit of work to do in terms of making it more efficient. But what is very surprising is that these other tools are based on very different ideas, and yet this data-driven approach with repair can solve almost every such instance that can be solved by other tools. I want to quickly highlight, along the way, we made lots of choices. So I have lots of plots that discuss the impact of the choices. But I want to highlight probably two of such choices. One is we generated the data. So one can ask, how does the quality of the samplers affect how many instances we can solve? So here I'm showing comparisons where you take the same tool and all you do is to just replace the different samplers. So cryptominicide is a set solver. So you can use a set solver as a poor man's sampler, just ask it to generate more samples. Quick sampler is another sampler that does not have guarantees. And CMSN is a sampler that we developed along the way because others weren't scalable enough. So you can see that the samplers affect quite a bit in what we are able to handle. Another case is about searching for nicer counterexamples. So typically it's, one is very eager to fix. You get a counterexample and you want to immediately fix with respect to that counterexample. Here it turns out that, finding a nicer counterexample using the max set and then repairing with respect to it is much better. There's again a difference of about 100 instances. So let me conclude. I think there are some interesting ideas here that would be nice to explore in other contexts also. So one of that is the prior approaches often started with some sort of abstraction. So, under or over approximation. Here, when we learn with the data, we make two-sided errors. So, and then we go on to repair it. So perhaps there is something to explore here. All the work we have discussed so far is in the context of propositional formulas. So it would be interesting if we can extend these ideas about generating the data, learning functions in more expressive theories, and then repairing it. There are also very interesting questions that are open from the perspective of learning theory. So all the work in the learning theory has focused on the case where there is an underlying function. So which means that for every assignment or input, there is over feature, there is a unique label. That's not the case here. And then even basic questions, what's the best way to generate the data? At least empirically, and it's also possible to argue that IID sampling is not a good idea when there are many possible valuations. So we don't know what's the best way to generate the data. What are the mistake bounds or complexity when you are learning functions from relations. So this is a setting that's very natural to us, but has not been studied in the learning theory literature. So I think studying some of these theoretical questions would be interesting. And I guess what also we found it interesting, over the period of 3 years from 2022 to last year when we did most of this work, that it turns out that we don't require the machine learning methods to give fully accurate solutions. So as long as they give us something that is good enough, it's possible to rely on the power of the set max set solvers to repair them. So this idea that we can use the formal methods for correctness and machine learning to quickly find a solution. So with that, I'll conclude. I'll be happy to take any questions you have. Thank you.
Okay, let's thank the speaker. Questions? Okay, let me then start off because I actually had one question, like how would you, when you said that you want to extend this to SMT, I mean, lots of techniques that you're presenting actually rely on the fact that you know that there are two solutions, either true or false. And do you think you could, what do you think could be extendable towards SMT, and what would need to be entirely redone?
I guess the most of the parts have to be done in the sense like sampling matters quite a bit. We have to generate these samplers, design samplers. How do we learn in theories? Here we could say that, okay, it's possible to learn the decision trees and then treat those as the Boolean functions.
Yeah, but like how you would create decision trees, you will need to have special predicates, right?
There is some hope because for LRA and all, one can possibly just use SVM and all as a separator. But it would be certainly more interesting when you had to use the theory predicates. The repair, I think some part of it can be indeed lifted. Some part of it we'll have to rethink what to do. Because some part is that, okay, this is the counterexample. find a nicer counterexample which agrees as much as possible with what we have. In the repair, I think there is, of course, already work on using unset cores. So I think it's out there, but of course, there's a lot of work that needs to be done to make it work.
Okay.
Yeah.
Are there more questions?
So in the relational description, the relational specification, you have choices of Y, but there are correlations between these choices. And as far as I understand, you learned that during the counterexample phase, right? Did you consider understanding these correlations before sampling in particular?
So that's a very good point. So something I should have highlighted, the correlations also come in when we are learning the decision trees, because what we do is that we learn the first variable you can learn in terms of everything else out there. But then when it depends on other variable, then you can't learn that variable in terms of to maintain this acyclicity. So we don't work with a fixed order of the output variables. And it's very, your observation is very right on spot, because we have tried lots of fixed order ideas that you first say that this is the order in which I want to learn, and then it doesn't work. So even in case of decision trees, it's important that the order is dynamic. But what we haven't explored so far is how to make it also influence the sampling, because in case of sampling, we do want to sample from like product spaces, because that's what the samplers can handle. So we don't know how to do that.
I'm asking because if I was the author of the relational specification, I may know what the correlations are. I may, for example, know that there is a group of Y's that need to take a particular value and another group of Y that need to take particular values, but otherwise you have cross products between these two groups.
Yeah.
And I assume that information would be useful to you, but maybe hidden from the formula from which you generate the relation.
Yeah, you are right. So right now the samplings, the learning stage is very inadequate, in the sense it just completely forget that there is a formula there. It says, I just want to look at the data, and it would be nice if we could combine the two. And we haven't figured out how to make it scalable. So I'd be very interested to discuss more.
Okay, last question, please.
Thank you. Maybe it's a bit related. You said at some moment that you do pre-processing and it's crucial. Can you expand a little bit? What do you do with your formulas?
There are lots of, I mean, some of the pre-processing that is done in set, you can still do here, finding backbones, constant functions, finding things that are uniquely defined. It's called independent support. So those things you can extract out of the like proof of unsatisfiability. So there's a lot of heavy pre-processing that is absolutely required. I can talk more. The entire. So maybe just before I conclude, there is one other thing that I was talking about is to learn without errors. So if you try to learn without errors, you solve about 170 instances. So you just force it to agree with whatever we have generated, then the performance is really bad. And this is where we were for a long time. We had almost lost the hope that it's not going to work until we allowed scikit to make errors.
Okay, so on that, let's kind of thank speaker once again.